Hello everybody. Till now we have been discussing about modeling of circuits, and in the last class we also did some analysis using the MATLAB software. Let me make a brief review. In modeling a circuit, we use the state space approach. That is, we define the state variables of the circuit or the system, which is basically the energy storing variable associated with the energy storing element in the circuit, like the C and the L. And after that we obtain the state equation. The state equation is of a standard form, which is x dot is equal to Ax plus B u, and the output equation y, which is equal to Cx plus du. Now, after having obtained the state equation, the state equations fully describes the dynamic behavior of the circuit. After obtaining the model, we input this model into MATLAB, and then we perform the analysis on by viewing in three different domains. One is the time domain. That is where the circuit and the signals, all these exist, that is versus the time axis. The other domain was the frequency domain, where you view the magnitude plot and the phase plot with respect to the frequency. That is, at various frequency, what will be the gain of the circuit, input to output, and what is the phase relationship of the output with respect to input. Now, these at various frequencies are noted down and plotted, and we use the Bode plot in MATLAB to check this out. And then the third domain, which is the pole zero domain, this is an important domain in the sense that you get the idea of the excitation modes, because the poles indicate the exponential growth or decay of any disturbance or noise which can occur in the system. So, a pole would mean e to the power of minus something t. Now, in the case of the particular example last class, we saw that for different parameters, for the same circuit, for different parameters, the pole locations can change. And we saw how fully damped system gradually became a kind of an damped oscillatory system, because the pole locations started shifting towards the imaginary axis, and it also became complex poles. So, various analysis can be performed on the circuits. Now, in this session today, we shall discuss one more important analysis, that is the steady state analysis, and specifically steady state analysis with respect to sinusoidal signals. That is, let us say the inputs are sinusoidal in nature, which is one of the most common inputs that you will be giving in the electrical circuits and electrical domain. So, for a sinusoidal input signal, because the components or most of the components that you will be using in the circuits are linear, you will see that all the branch currents, node voltages, they all will be sinusoidal. However, there will be phase shifts with respect to the input voltage that you will be applying. Now, how do we characterize the system under steady state condition under the constraint that sinusoidal inputs have been given? Some important features of the circuit can be extracted in this mode. So, today that will be the focus of the discussion. Given a sinusoidal excitation under steady state condition, how will the system behave? Of course, it is a very specific nature. The problem is a very special case. The state equation is a more general case. You can apply the special case to the state equation and obtain the steady state equations. Of course, we will see how we go about doing that in this session. Before that, we have to understand the concepts of the J, the rotation factor, which will be used commonly in the steady state analysis. So, let us try to understand the concept of the cos and the sine rotation. Now, let us consider the time domain axis. So, I am having a y axis here, and likewise I will also have the x axis, and the x axis is time t. Now, here on this x axis, let us say that we have a sinusoidal signal like this. Okay. So, let me call this one as V A. This is the sinusoidal signal. Now, the sinusoidal signal can also be imagined as a phasor which is rotating in the complex frame. What I mean to say is, let us have alongside here a complex frame, okay, aligned along this axis. Okay. This also has a orthogonal axis, which is the y axis. Okay. Now, this being, that is, you have the real and the imaginary. So, I will call this one as sigma and the imaginary axis. Now, imagine that there is a vector along this action. Now, this vector, we are going to make it rotate in a circular fashion like this. So, this vector is going to be made to rotate in a circular fashion like that all along. Now, we are going to just note down the projection of this vector on the vertical axis, and that projection value will be projected onto this time axis as shown here. So, let us see what happens. So, let us say now at this point the projection of this vector at this point is going to be 0. So, let us say this is a point here. Now, let us say this vector has taken a position here. It has moved to a position here. Now, this is the projection along the vertical axis, and we project it along to this, and we have a point here. And let us say this vector is now moved and taken this position, and its projection on the vertical axis, and then taken on to this, because this is occurring at a time which is much later than this. This is occurring at a time which is much later than this, and therefore, the time progression of these points, and so on. And you will see that we have the peak occurring at this point, that is when this vector is 90 degrees in the complex frame. So, therefore, you see that there is a phase shift of there is a phase shift of 90 degrees here also in the time domain, the 90 degree point with respect to the 0 point. So, so on. If we keep writing all the vectors, we get the various points which on projecting to the time frame will give you the various points here, this and so on. So, we can say the sine wave can be considered equivalently as a phasor or a space phasor. We will call this a space phasor because it is in the complex domain and it is rotating continuously in a circle. The amplitude is fixed and that amplitude is equivalent to whatever our maximum amplitude here, let us say this is Vm, and that amplitude is also Vm. So, with an amplitude of Vm, this is rotating, and if we just keep taking the projection on the vertical axis and then project it all onto the time axis, we get the sinusoidal signal evolving out of this one. Okay. Now, let me consider another space vector simultaneously. When the blue is at this point, I will say that there is a red space vector at this point. Okay. The blue was called VA and let us say the red is called VB. This also has the same amplitude Vm, and with the amplitude Vm, and this is also starting to rotate, this is also starting to rotate, and once the whole cycle is completed, one period is completed here. So, which means the red space vector on projecting will start from here at time 0, when the blue space vector is starting here, the red space vector is starting here at time 0. And then you would of course have, after some time, this would have come to this point and then its projection will, let us say, be along this curve. So, we have something at this and then the vector will progress in this fashion. You have a point here and then the vector progresses here like that, you have a point here and so on. So, we see that we will be obtaining a wave something like that. And keeps going on to like this. So, you will have a point here at different corresponding points, point here, of course, this is how it will look like. So, if I am having a space vector starting 90 degrees away from the VA space vector, okay, let us say I have a vector VB which is starting 90 degrees offset or 90 degrees phase shifted with respect to this VA space vector, then you see that the resulting time projection of the space vector tips is a cosine wave. So, what you get here VB is a cos wave. So, VA is a sine wave and VB is a cos wave. Now, let me go to the next page, but before that let me select the wave pattern . And then, oh sorry, I didn't copy it. Okay, let me select the whole thing I'll copy, go to the next page, let us paste. Now, if you say that VA equals Vm sin omega t, isn't it? Vm sin omega t, amplitude Vm and sin omega t. Vb is Vm cos omega t. Or we could also say that at every instant of time the VA space vector and VB space vector are shifted by 90, that is, are phase shifted by 90 degrees. So, you could also write VB is VA into a phase shift of 90 degrees e to the power of j pi by 2, 90 degrees, which is equal to VA cos pi by 2 plus j sin pi by 2. This is 0, of course. This has a value equal to 0, was not there. This has a value equal to 1, and therefore, you have which is equal to j VA. So, therefore, if we have VA is equal to sin pi by 2, Vm sin omega t, and Vb equal to Vm cos omega t, we could also say that Vb is equal to j VA, or which is equal to j Vm sin omega t. This is a useful relationship which you will be using a lot in the sinusoidal steady state analysis. Where will we come across such a thing? Now, let us say, for example, we have d by dt of VA, which is equal to d by dt Vm sin omega t. This is equal to Vm omega cos omega t, which is equal to omega into Vm cos omega t, which is equal to omega into j Vm sin omega t, or which is equal to j omega VA. So, d by dt of VA is going to result in j omega VA. So, what does it mean? That wherever you have d by dt, you are going to get this term. So, we can have a mechanism where we replace d by dt's with j omega to obtain the sinusoidal steady state equations. So, in the state equation, wherever there is d by dt, replace it with j omega. That will give you the sinusoidal steady state equations. We will see that shortly. Now, we have two major dynamic components, which is the capacitance and the inductance in the electrical circuits. the capacitance which is storing the potential energy and the inductor which is storing the kinetic energy by virtue of the flow in it. So, let us consider first the capacitance. So, we have the capacitance here C. There is a flow of current through the capacitance, let us say IC, which is going to result in a voltage across C, and that is Vc, with this positive and this is negative. So, for this dynamic element C, what is the equation? We have C dVc by dt is equal to IC. So, this is what we started with. Now, suppose all the quantities were sinusoidal. So, if the quantities are sinusoidal, then Vc will be a sinusoidal function, something like Vm sin omega t minus phi or something like that. So, it could be something like d by dt Vm sin omega t minus some phase shift, arbitrary phase shift, let us say. This is equal to IC. Now, here we are operating by d by dt. So, when you differentiate Vm sin omega t, it is going to be Vm cos omega t minus phi with an omega term coming into the picture there. So, it will be omega c Vm cos omega t minus phi, or this can be written as omega c j into Vm sin omega t minus phi, or we call it as j omega c into Vc, and this is equal to your IC. Now, notice this equation, j omega c into Vc is IC. This has a unit of amps, this has a unit of volts, isn't it? This is volts, this is amps. So, what should be the unit of this? So, it should be something connected with the ohms. So, we know that we have a volts divided by ohms will give you the units of amps. So, we have Vc into j omega c, which is IC, or Vc divided by 1 by j omega c is equal to IC. So, therefore, comparing these two, Vc is volts, IC is amps, this should have the units of ohms, and this we call it as reactance or capacitive reactance. Of course, there is a j term. So, 1 by j omega c can be written as minus j by minus j square omega c. Minus j square is 1, therefore, we have minus j into 1 by omega c. So, this we call it as capacitive reactance XC, XC. And there is a phase shift which is corresponding to this J here, and the minus J, which is a minus 90 degrees rotation in the space vector, which would mean it leads, that is, it occurs before the normal phase vector. So, therefore, this has a leading effect, and here we have capacitive reactance. The capacitive reactance, and that is JXC, which is this, and this has a unit of ohms. XC is 1 by omega c, J is a rotation parameter in the complex domain, and minus is to indicate that it is a leading phase, not the lag. Now, consider the other energy storing element, which is the inductor. An inductor L, which has the state variable IL flowing through that, and there is a voltage across the inductor which we will call it as VL. The dynamic equation for the inductor is L DIL by dt, which is equal to the voltage across the inductor, which is VL. L DIL by dt is equal to VL is the voltage across the inductor. So, if the current, the state variable through that one is a sinusoidal quantity, then you have L d by dt Im, let us say sin omega t minus phi, which is equal to VL. Even VL will be a sinusoidal quantity with a phase shift, of course. Now, we see here again along the same way we have a d by dt. I can replace it by j omega. So, you have j omega L Im sin omega t, which is IL, which is equal to VL. So, here you have the voltage VL, which has a units of volts, the current here having a units of amps. So, volts will be amps into ohms, and therefore, we can say that this should have a unit of ohms, and that factor j omega L into IL is equal to VL. This factor is written as JXL, and it has a unit of ohms. So, XL is equal to omega L. This is called the inductive reactance. And see the rotation, the positive j there, which means that it is rotated positive in the positive direction by an angle of 90 degrees, and with respect to the capacitive reactance it is 180 degrees, because capacitive reactance gives a minus 90 and this gives a plus 90 and it is 180 degrees. In fact, it is very evident in the case of the pole 0 plane. You will always have complex pole mirroring along the real axis. So, you will have if you have a pole on the left of top, you will have a corresponding mirrored pole on the left of bottom, and there is a 180 degrees phase difference between these two, to indicate that there is a resonance action, and the resonance can actually occur, an oscillation can only occur if there are two different types of energy storing elements, which is one which is kinetic based and other which is potential based. So, anyway, coming back to the equation here, we have the inductive reactance which is written here. So, summarizing, we have for the steady state sinusoidal condition, should remember that only for the sinusoidal condition, and for these two components C and the L, this is going to provide a resistance or an impedance which is given by minus J X C, and this is going to provide J X L. X C is 1 by omega C, or I could write as minus J 1 by omega C, and this is J into omega L, where C is the capacitance value and L here is the inductance value. Omega here is nothing but 2 into pi into F. It is radians per second. This frequency F here is in hertz, written as Hz. So, at any particular frequency, radian frequency, the capacitance provides a reactance which is 1 by omega C, and for the inductance at any particular frequency omega, the reactance provided by the inductor is omega L. So, if you look at this here, at omega is equal to 0, what does it mean? When omega is equal to 0, this means the signals are DC. So, at omega is equal to 0, observe that this tends to infinity, because omega is at the denominator, which means capacitance provides very high reactance, infinite reactance, which is basically the reason why the capacitance blocks DC. And in the case of the inductance, at omega is equal to 0, there is no inductive reactance, it is appearing as a short, which means that the inductance has saturated, it no longer provides any at DC, it does not provide any impedance. This will be 0. Now, at omega tending to infinity, very high frequency, very high frequency, omega becomes very high. So, during that time, the impedance or reactance or the impedance provided by the capacitance is very negligible. So, this will tend towards 0 at high frequencies, which means it provides a very low impedance path at high frequencies, and at high frequencies the inductor gives you a very high reactance or impedance, and this tends towards infinity, which means it tries to block high frequencies. So, which means it will drop across it all the high frequency, this will pass all the high frequency components, whereas on the lower frequency side this is going to pass the low frequencies, whereas this is not going, that is, this is going to provide a high impedance at low frequencies, which means it is not going to pass low frequencies, and this will pass the low frequencies. Okay. This is one of the important feature that one can know about by studying the steady state character. Now, let us look at this simple equation which is obtained from this circuit. So, you have an R and let us say we have a C. So, we have an R and we have a C, and let us say we have a Vi which provides voltage in this fashion. Let us say we have a voltage here and of course a voltage here. Now, R is going to provide a resistance, C is going to provide a reactance, and that value is minus JXC, which is equal to minus J by omega C. That is the reactance this capacitance is going to provide. Now, what will be the current which flows in this loop? What will be the current that flows in this loop? It is nothing but the voltage divided by whatever comes in series. Now, R, what comes in series, all the impeding parts would be R minus JXC. Now, this is called the impedance Z. So, the current I will be nothing but Vi by Z, the impedance. Now, this is also having a unit of ohms, which is basically nothing but Vi divided by R minus JXC. R is equal to Vi by R minus J by omega C, to include the omega and the capacitance values in the equation. Okay. So, this is the steady state value. One could also obtain, should note that the state equation is the most general, and this is a specific case or the special case. Let us look at the state equation of this particular circuit and then see if you substitute the j omega for the d by dt's, you get back the steady state equations. So, you will see that for this circuit we have already obtained the state equation in a previous session. In a previous session we have Vi, this is R, this is C, we have a voltage and the voltage across C we see, which is like that. Okay. So, the state equation is dVc by dt is minus 1 by RC into Vc plus Vi by RC. Now, the step is that for all the d by dt's you just replace by j omega. In fact, for whatever be the system which is represented as x dot, which is equal to Ax plus Bu, the dynamic equation part of the state equation, you can replace this by j omega x. That is what we are trying to do here. So, we have j omega V c which is equal to minus 1 by r c V c plus 1 by r c V I, and let us take c on this side, becomes j omega c V c which is equal to minus 1 by r V c plus 1 by r V I, and we know that this is nothing but the capacitive reactance part, which can be written as V c by minus j x c, which is equal to minus 1 by r V c plus V I by r. So, this when you rearrange it, that is, you take V c on this side and then on rearranging you obtain, let us have this circuit with us, copy, let us paste it here. We will obtain by rearranging that V c will be V I by r minus j x c into minus j x c. You see, this has a reactance minus j x c. Now, the current through this is nothing but V I by r minus j x c. This is the current through that. This is the current through this loop I into the reactance, into the reactance current into the ohms, which will be the voltage across that one. It will be straightforward analysis, and this is being obtained directly by the original state equation. So, state equations can be brought into the steady state format, steady state equation analysis, just by replacing d by dt with j omega. Likewise, if you see the inductive circuit also, we have R and an L, a VI, this is the R and the L, and of course, here the state equation is IL. We have L dIL by dt equals VI minus IL into R. So, this is basically the state equation which was formulated. This actually is not the full complete state equation. State equation is always the dynamic equation plus the output equation, but I mean that we need to consider only the dynamic equation here to obtain the steady state relationship. So, this portion, this is the d by dt, we replace by j omega. So, what do we get? We get j omega L into IL, which is equal to VI minus IL into R. So, what is j omega L? Nothing but j to XL. You see that omega L is the inductive reactance into IL, which is equal to VI minus IL into R. So, take IL into R onto this side, you see that VI equals IL into R plus J XL into IL. You see, this is the voltage. IL into R is the voltage drop across the resistance. JXL into IL, voltage drop across the inductance, which is VL, and we have VI, which is here. So, KVL is observe that the KVL is obeyed here, that is the summation of the voltages, instantaneous voltages VI, IL into R and JXL into IL, they all sum up to 0 every instant of the time. Therefore, the Kirchhoff's voltage law is obeyed even under steady state conditions, so that the energy conservation principle is still held. So, this portion is the inductive reactance. So, if I take out IL, it becomes R plus JXL. So, this is the inductive reactance, this is the resistance portion. Together you have a complex impedance Z. So, VI by IL, which is equal to Z, the complex impedance, which is R plus JXL in this case. So, actually analysis can be done from the state equations, but we know that we are going to do only sinusoidal steady state analysis. You can directly do the simplifications on the circuit. For example, let us say we take a circuit like this. You have R, you have L, you have C, you have, let us say, another R, which is drawn like that. So, this is R1, L, C, R2, and then you have a VI. Now, this L is providing an impedance which is JXL or J omega L at that frequency. And for the case of the capacitance, it is providing minus JXC, which is nothing but minus J by omega C. This is the impedance that is providing. Now, you can just make all the analysis with just these variables on your circuit. So, you have VI the voltage source, R1 is the resistance, JXL is the inductive reactance, minus JXC is the capacitive reactance, R2 is the resistance which is connected across the output. So, for example, if one needs to know what is the voltage across the output, which is basically this value. So, we have in simple terms like what you would do for a resistance, R2 parallel minus JXC divided by R1 plus JXL plus R2 parallel minus JXC. This is the attenuation factor. This impedance divided by all the impedances taken in series is going to be the attenuation factor into Vi will be your V naught. So, this is the input output relationship for sinusoidal excitation Vi at the frequency omega, at a single frequency omega, given as such under the steady state conditions. One could also use to find what is the impedance as seen from here. It's also an it's also a interesting thing to view or study. Let us say we have this we take that circuit, copy, go to the next page, let us paste, push this a bit above. So, let us say we have the circuit here, we need to find what is the impedance as seen from here, that is what is the impedance as seen from here. So, which basically means that if this was not there, we just have this portion of the circuit and we would like to see what we are seeing as an impedance from here to the output portion. So, it is nothing but this in series with this in series with these two together. So, which basically would mean R1 plus j XL plus R2 parallel minus j XC. These three in series is going to be the, now what does this imply? This basically means that this is R2 minus JXC by R2 minus JXC plus JXL plus R1. This is equal to Z. Now, this can be further simplified into real and imaginary parts to get the complex impedance. Now, let us take this equation. Let me copy that. Let us go to the next page. Let us paste that, push that above. Now, this can be written as R1 plus JXL plus minus JR2XC divided by R2 minus JXC, R2 plus JXC, R2 plus JXC. This is a algebraic manipulation, so that we try to eliminate this. So, if you see this, this will be R2 square minus J square XC square, all other terms cancel, and therefore, we have here R2 square plus XC square. So, there are no J terms here, we want to put all the J terms to the numerator, and here you have R2 square XC minus J plus J square R2 XC square. There is a JXL here and an R1 here. Okay. So, this portion here is 1. So, that becomes a real component R1 plus R2 XC square divided by R2 square plus XC square, that is the real portion, plus J XL minus R2 square XC divided by R2 square plus XC square. So, we have basically split the whole impedance into a real part and an imaginary part. This is equal to our Z, the complex impedance. This is the complex impedance of this circuit as viewed from the input. So, this is nothing but the input impedance. Of that circuit. So, this is some of the types of the analysis that one can keep doing with the sinusoidal steady state models. So, with that, let us conclude this session. Thank you.